Hi, hello, welcome to late section. Ooh, so sorry we're starting late. It's been a morning. And then if someone tells me what the question is for today.
It's just how are you feeling?
In a few words. So I'm going to ask y'all some questions about the exam that are kind of the things that I care most about. I want kind of like thumb answers. So, one, did you feel like you were prepared for the format of the exam? Like you knew what you were going to be tested on? Okay. Do you feel like the exam questions were comparable in difficulty to the practice exams or PSET challenge problems? And then the other question I have is like, what other resource would have helped you? Like, if we could have made something else, like this year we made the solutions video for the practice exam keys. Where? That was a suggestion on the mid-semester feedback last summer. So we have them for exam 2 and the final practice exams. But yeah, like we want to make resources that are going to be helpful for y'all because in our heads right now, like the exams are pretty consistent in terms of what we are writing. Like I literally was just looking back at the past 6 years exams and I said, what would fit in this crowd? Um, but yeah, those are kind of the big things that we care about here. But I do want to hear feedback. We are going to do a more involved like mid-semester feedback, and we'll give more details on it next week. And then the week after that, I do my mid-semester check-in meetings with everyone, where I will be meeting with everyone in the class. We will do 10-minute meetings in Smith, and it will be very like, hi, what's going on? Okay, let's get into it. Like,
So that's like 700 minutes.
it's a time. It's a time. I enjoy my job. But more details on that will come. For right now, I think the big thing that we can do is we can, yeah.
I'm just thinking maybe we have those top videos for the PSETs in afterwards as well.
Like challenge problem solutions. Yeah. Mm. It's a good suggestion. Yeah. I tried to at least do that for the synthesis questions. Like, yeah. I'll keep that in mind. Maybe it might be something of just like the mechanisms and synthesis, like or mechanism synthesis box, like the kind of like reactions heavy ones. No?
It could even be like in help room on Mondays when people come and like most people have the same questions in terms of challenge problems. If there's one specific one that people like need your guidance on, you can like do it. We can all do it together on the board and just record that so that you don't have to like sit down again and like.
Yeah. It's also the thing when I do it with the class, there are like more questions that come up, and so if you're watching back as a review video, like I'd probably record it separately either way. But like there are ones each year that I plan on doing in help room with everyone with like a group of 20. Also, there weren't many people at help room on Wednesday. There were like maybe 5 people, maybe. Like at one point there were 2 people. I was like, oh, what? It was 2 to 5:30. Yeah. Yeah, it's okay.
I think at that stage you're just like locking in on your own, like putting it all together.
Yeah, no, and that's what I figured. Like, yeah. Okay, so, yeah.
Like another thing is just like if we just had like a bunch of like box like mechanism and synthesis questions that we could just like do.
The hard part is, like, we have more exams. Like, we could release 5 practice exams, but then it becomes a trade-off. Well, some students, like, I know you're on it and, like, can work through all of those. But, like, the PSET 2 was due on Monday night, and Thursday's exam, and you have a whole new lecture in between. And, like, it does seem a little unreasonable to give, like, 3 or 4 practice exams, because then you think, oh, I have to work all those.
Honestly, the first thing that occurred to me when you said like what would be helpful, I was just like more time, but that's impossible. Like,
Yeah.
That's the limiting factor.
Yeah.
It's so.
But be thinking of things. If you have other ideas, let me know afterwards. Let's go ahead and jump into kind of content things. So there are 4 big parts of Lecture 5. We have imine, enamines, we have redox, we have carboxylic acid derivatives, and then we have amino acid chemistry. So we'll go through them, and my goal is to hopefully get through some of the challenge problems with y'all just to save you some time for like the weekend. So I'm going to plan on going until the 45 because I started at the 45. Is that okay? And if you need to leave, leave. It's all good. Cool. So, yeah, this is my favorite of the memes today of like the nitrile, all the other CADs, and we just include the nitrile. It's a little, Or know the difference between an enamine and an amine. Self-absorbed, flawless. Never mind, just me. I'm the only one that found it funny. Cool. So, let's talk about amines and enamines. So first off, we have some new functional groups. So we've seen before carbonyl, and we've seen this a new functional group in enol, where we have an alkene and alcohol. And what we have in lecture 5 is the nitrogen version of these. So we have the imine, a CN double bond, and an enamine. It's like an ene and an amine. Wow. Then we also have our labeling, like this is where our nomenclature for amines came in, of like we have the distinction between a primary amine and a secondary amine, which is just how many carbons the nitrogen is attached to. So let's look at the mainline reaction, and we'll come back to some of this in a minute. So if we start off with a ketone aldehyde, and we react it with a primary amine, then we get an imine. But if we react it with a secondary amine, so 2 R groups on our nitrogen, then we get an enamine. And so that's going to be the big distinction of which one of these 2 reactions we wind up in. The mechanisms are largely the same. Like, they all have the same first 4 steps, and then the last step is slightly different. So, first off, you just attack the carbonyl, you get to your tetrahedral. We do a proton transfer, and we get to this neutral intermediate that is called a hemiaminal, which the first time I heard that term, I was on this floor. I was like in another classroom on this floor. There was a review section, and I heard the TF say hemiaminal, and my gut instinct was gesundheit. Because that's a fake word. Like, that's an involuntary utterance. That's something that just, like, fell out of your mouth. Hemiaminal. Like, stop that. So it is absurd. We are on our bullshit here with this name, hemiaminal. But she always appears in these mechanisms. She's always going to be like a neutral intermediate that pops up. And the reason she always appears is because she is neutral, she is a stable intermediate. So we see her a lot. From there, we need to kick off the water because in our products over here, we don't have oxygens anymore. So we do a protonation to make a good leaving group. Then we do a lone pair push, kick off the water. So once we reach this point, we are at pretty much an aminium. So if we had a primary amine, we'd only have 1 R group on it, and we would have an H. And so our last step would just be a simple deprotonation to make a neutral amine. However, if we start off with a secondary amine, when we get to this point, we're still going to have 2 R groups on it. So there's not something that we can easily deprotonate on the nitrogen. So in this case, what we have to do is we have to look next door at the neighbors. So this is where we get into our other piece of nomenclature, which is like alpha, beta labeling. So if you have a carbonyl or an imine or some sort of double bond like this, we say the position right next door is called the alpha position. So in this case, this is an alpha carbon, this is an alpha carbon, and on the alpha carbon, we have alpha hydrogens. I tried to bring up this label when we talked about conjugate addition. I said the last step was an alpha protonation. That's because we're going to be using it for here. And you can even go out further and like this is a beta carbon. If you had another carbon, it would be gamma carbon, and then I think a delta carbon. But you really only need to know alpha and then occasionally beta. Yeah.
Why do you say that we had to do the alpha, what is it called? Alpha
Protonation?
Like, what about the nitrogen in this state?
Oh, I'm about to get to that. Yeah.
The same numbers like a second alpha carbon.
No. It's the alpha and beta is an alternate to using numbers. So like it is just, and this is the frustrating thing. Like a lot of it's just convention of like if we have carbonyls or if we have amines, the convention is to call it alpha beta rather than use numbers.
So just use any like alpha, I have to assume that it's either one.
Yes, they both are. Yes, and so you'll have a choice if there are two alpha carbons. Yeah.
Is that convention because if you had a really long carbon chain, you wouldn't want to start all the way at the end for the numbers?
Something like that, yeah. Cool. So what we did in the past when we did conjugate addition, the last step of conjugate addition was we had an O minus, we pushed down, and we grabbed a hydrogen that added at this alpha position. So we called it an alpha protonation. But here, when we are in this secondary amine case, we've gotten to this point in the mechanism again where we have the double bond, but now we don't have anything that we can easily deprotonate over here because we have two R groups. So this alpha hydrogen is actually something that we can deprotonate with our solvent and push in and push up, and then it makes a neutral enamine as our final product. So it's essentially a strategy for the molecule to become neutral. So again, all of these follow the exact same steps, but just differ in this last one here. One thing with this proton transfer, very specifically, there are like two common misconceptions. One common misconception is people think that this hydrogen, this specific hydrogen, just goes over here. So like it's something like this. It's just not going to react that way. Like hydrogens come on and off because this molecule is bumping into a lot of other molecules. So they're not the same hydrogen. And then the second thing is people are like, well, proton transfer, then we're just doing a protonation. So why can't we just do proton transfer and just go from here to here? And the issue with that is proton transfers are very specifically one deprotonation, one protonation. Nothing else. Like otherwise you can't really call it a proton transfer. And also going from this structure to this structure, 3 hydrogens need to be added or removed. So like it's just, again, it's kind of conventions, but it takes a minute to get. Any questions on the proton transfer and why this would not be a good proton transfer? Fierce. So we also have the reverse reaction for both of these, the hydrolysis, where if we start with an amine or enamine, we can add H3O plus and get back to our ketone or aldehyde and then some type of amine. For this one, it's the exact opposite, so I'm not going to go through it beat by beat, but I will just note that the first step for both of them is a protonation. And do you see how these are exactly undoing the deprotonations up here? Like for the amine, you protonate at the nitrogen, you get back to this structure. For the enamine, you do an alpha protonation. So it's just straight up doing the reverse, and then all the other ones are the same. The protonation states are a little bit different here because you have it happening H3O plus. So when you push down over here, you'll wind up with a protonated amine that needs to be deprotonated. Or sorry, words, a protonated carbonyl that needs to be deprotonated. But let's kind of put this into practice. Yeah.
Can you explain how come at this stage, step 4, where does H come from?
We're in H3O plus.
So between step 3 and step 4.
The whole time.
In the solution.
Yeah, the whole time this reaction is happening and H3O plus is around.
No, I mean R2HN.
This?
Yes. From R2 to N to R2HN.
Oh, that's a typo. Thank you. So sometimes the formatting in ChemDraw, it does weird things, and I'll just add a hydrogen out of nowhere. So yeah, this should be R2N again, and then it's protonated in R2HN. Good question. Yeah. So I want to look at a hard question with this, and this is our first practice of the day. The amine-enamine mechanism. This is a skill builder, but it's a challenging one because it just does not look any kind of normal. So first, let's kind of analyze this and figure out what's going on. What functional groups do we have in our starting material? Aldehydes. And then we have an amine here. And my question for you is this a primary amine or a secondary amine? It's a primary amine. because this nitrogen is only attached to one carbon. The Lewis structure would look like NH2, CH3. Okay, so it's a primary amine and an aldehyde, and we know that that should make an imine, right? Primary amines make imines. So we should be able to draw some products, or draw some curved arrows, and get to a nitrogen here with a CH3 group on it, which I'm just going to write as Me. So going from here to here, this should be straight up copying the arrows from lecture that you've seen before. So can I give y'all like 3 minutes to try to draw the curved arrows to get to this point? Try it out. That should be an intermediate on your way to this. No, but not generally. So R, we typically mean carbons. How's it going?
I didn't know you were gonna.
Work. In that case, let's do the steps of the amine reaction together. So, the first step on our amine reaction, and I'm literally just like straight up looking at this right here. It says the first step is the amine attacks the carbonyl. So let's do it. The amine attacks the carbonyl. Second step, proton transfer to the neutral hemiaminal. So we make an OH and we make an NHMe, so now they're both neutral. Third step, protonate to make OH2 leaving group. Fourth step, lone pair push from amine to kick off water. Lone pair push down, kick off water. Fifth step, deprotonate to neutralize. Does that kind of track in terms of like when I say it's going to be straight up the arrows from the section, it means like all it is mapping these molecules onto the exact curve arrows that were drawn in lecture. And it takes a minute to get that matching skill to where you can do it quickly. Like a lot of y'all, like it will probably take more time than when I just drew it out here, because you're thinking about, okay, what is still connected to this molecule? How do I write this out like efficiently? And a lot of it, just the speed comes with time. But any questions on how we got here? Okay, it's about to get worse. So let's try to map this material that we're at, this intermediate, onto our products. Is there anything that you see as like a defining characteristic, feature, or atom that you're like, I'm pretty sure this thing in the intermediate is this thing in the product? Yeah.
Like the nitrogen.
Yeah, the nitrogen and the ME. So if we have this right here, it seems pretty certain that this is this. Okay. But then, what would this carbon be? Well, I guess it could be either one of these, and it's symmetric. So does it matter whether we call like this red star over here this, or if we put it over here? No. So let's just pick one. Because it's symmetric, it shouldn't matter. Ooh, so okay, then I'm going to do some numbering here. So we have a 1, 2, 3, 4, 5 membered ring. And the nitrogen's going to be 1 here. And if I number 1, 2, 3, 4, 5, I see that this one on the other side, the carbon that's currently the aldehyde, needs to wind up bonded to the nitrogen somehow. That is the really weird step. And like the one step in this that I think would be the hardest one to predict is the one that we are about to do, which is, well, carbonyl is an electrophile, right? Doesn't this imine still have a lone pair? Couldn't this imine just, boom, crazy wild. We are used to, for this reaction, amines attacking carbonyls, but an imine could. And actually, you saw this in the exam. This lone pair on the imine on the exam, or I think I just used an H on the exam, so NH da da blah blah. It just went and attacked the empty p orbital on AlCl3. So, special, fun. I don't know if it's fun. But, so we are attacking our carbonyl. Now, let's use this number system here to help us just draw what the next molecule is, because I think cyclizations are hard to draw. So if we know we are connecting 1, 2, 3, 4, 5 atoms, all we need to do is do a 5-membered ring, and then one of the atoms is going to be nitrogen. So I'm literally just going to draw a pentagon, and I'm going to make the nitrogen in one of them. I'm going to use my numbering, so I called this nitrogen 1, and then I'm going to number it 2, 3, 4, 5. So if I do it this way, what should be on carbon 5 after these arrows? Well, now it's going to be single bond. Yeah, so we have an O- on it. Okay, and then on our 1 nitrogen, we should have a methyl, right? Then 2, between 1 and 2, we should have a double bond. 3 and 4 are boring. So that's kind of beat by beat a strategy that uses some anchor points with like numbering here that can help you write what the next structure is going to be, even if you can't kind of fully visualize it all at the same time. And then anything else we're missing on this structure? Nitrogen needs a positive formal charge because it has 4 bonds. Cool.
put the formal charges in circles?
No, I just like it to make it look neat. Yeah. Okay, so what we're going to do, we need to get rid of these charges. So first, let's just go and grab a hydrogen for this. So now we have an OH here. We have our Me plus. And then when we had a nitrogen, or kind of an iminium situation here, with a positive charge, and we couldn't deprotonate the nitrogen, where did we deprotonate? I'm thinking more about when we had a iminium situation here with a nitrogen, an alpha hydrogen. So it looks kind of weird, but let's try to find an alpha hydrogen. So if this is our imine bond, the carbon one next door is an alpha carbon. Yeah. So if this is our imine CN bond, the carbon one next door is an alpha position. So like normal way that you're used to seeing it is CN like this, and then here these are the alpha positions that are one away. But here it's weird seeing it in a ring. So what we're going to do is our solvent's going to come along and do an alpha deprotonation. And it looks weird, but it is arrows that you've seen connected to these molecules and their chemistry. So we have the Me to N. Now we've made a double bond here. And I think we are neutral. Okay, so it looks like we're getting more close to here, right? We've made some progress. Our molecule at least starts to look like the end. So things that we have remaining to do, like chemical goals, bonds to make and break, we should make another double bond over here, right? Because we need to have 2 double bonds in this 5-membered ring. And we need to get rid of this OH. Well, another weird thing, if I have a nitrogen something and an OH attached to the same carbon, what new functional group is that? The Gesundheit, the hemiaminal. This is the one where it's hard to spot, but it's kind of like a hemiacetal, where you have an OH, and instead of an OR, you have an NR kind of situation going on over here. So this is kind of halfway through another imine reaction. So when we were at the hemiaminal and the imine reaction, actually we have it right up here, hemiaminal. What we did was we protonated and we did a lone pair push to kick off water. Let's try to do the same thing. We have to kick off the O somehow. So here, let's protonate our OH. You want to kick off the oxygen somehow. And so to make it a better leaving group, we're protonating it. So this step that we just did is a mimic of this one up here, both in the squares. And now we need to mimic this lone pair push here. So who's going to be our lone pair pusher in our current molecule down below? The nitrogen, yeah, because the oxygen is what we're trying to kick off. So we are going to push in and kick off. And I did mean to do all my curved arrows in red just to make it poppier, so I will go and color them and give you a chance to draw. So now we are so close to the end. Now we are yet again stuck with a positive charge on nitrogen that we can't easily deprotonate. So when we are in that situation, where do we start to look? We look for alpha hydrogens. This is just like the last step of our enamine reaction, where now our nitrogen has all carbons bonded to it. We can't deprotonate it. So if this is our imine, we go one carbon next door and find our alpha position. For this imine, it's one next door. So we are going to have our solvent come and do an alpha deprotonation, taking the electrons from that single bond, making a double bond between carbon, and then pushing up the electrons back up to nitrogen. And we are done. So I think the big thing to see here is that, like, firstly, this part was just the reaction from lecture. And then every other step that we did, except for this one step in the middle, every other step that we did was a step that was in the amine or enamine reaction mechanism. We were protonating an O. We were doing an alpha deprotonation. We were protonating an OH to make a better leaving group. We were doing a lone pair push off the water. We're doing an alpha deprotonation. The hard part is not actually doing these zeros. It's clocking that this is the same scenario we've seen before. And that is the thing that you are going to be practicing as you do more problems. Yeah.
So do you ever use the beta hydrogen?
So, lecture 10.
Oh, okay.
Yeah. Yeah. It's coming. Like, that's the reason I told you it, just to preview that she's coming.
Okay, but for now it's
For now. Yeah. But beta hydrons, crazy stuff happens.
no.
Crazy stuff. It's my favorite lecture, I think. Lecture 10. Cool. Any other questions on the amine stuff before we move on? This was a hard example. I really said, let's go straight from the exam into one of the hardest mechanisms on the problem set. Yay. Woo. Okay, so let's pivot. Let's talk about the redox line reactions. So first off, do you remember in like Gen Chem calculating like oxidation numbers and like there were all these rules and everything? We're not doing that. We're not doing that because organic chemists are what? Lazy. Thank you. So we have a shortcut for figuring out the oxidation level, which is a little bit different from the oxidation number. In oxidation level, we primarily are concerned about carbons because, again, organic chemists. So we describe the oxidation level as the number of bonds a carbon has to electronegative elements. So the highest level that we can get is carbon making 4 bonds. That would be like a CO2 or like a carbonic acid over here. Then we have oxidation level 3, where we have like a double bond and then another situation here on the side. And these are our CAD family that we saw in like lecture 5, a lot of those reactions. Oxidation level 2 are ketones and aldehyde, which is a lot of the lecture 3 stuff that we talked about. And oxidation level 1, alcohols, amines, alkyl halides. So things that are in the same oxidation level react similarly, which is why this is a helpful structure for us. Like this was lecture 3, this is lecture 5, this is lectures 6 and 7. Like it really, this is how we think about how molecules react their oxidation level in a lot of ways. So redox reactions are reactions that are going to move things into different oxidation levels, either moving up oxidation levels, which we say is an oxidation, or down oxidation levels, which is a reduction. And we have some heavy hitters on the team this season to carry out our redox reactions. Our main oxidizer is going to be chromium trioxide, also called the Jones reagent. Now, she is from the Earth. She's chromium. I'm trying to like give her background, her story, and I realize I don't really know much about chromium. But she's great. She's really helpful. And then her sidekicks are either going to be pyridine, which is this 6-membered ring with a nitrogen. It's kind of like what if a benzene had a little nitrogen spice, or water. So those are her sidekicks. On the other end of the coin, we have lithium aluminum hydride, which you've seen. You know her. You love her. One thing, I want to tell you her nickname. We haven't told you because we didn't want to confuse you, but lithium aluminum hydride's a mouthful. isn't it? Like, it's hard to, it doesn't roll off the tongue. Lithium aluminum hydride. Like, no. So oftentimes we'll just call her LAH. Yeah, it's a bit much here. Don't write LAH on an exam, but if you need to talk about her, you can call her LAH. Yeah. So they are going to be doing a lot of heavy lifting for us in synthesis and line reactions. And I'm wondering if we could just take a moment and give them a round of applause for their hard work and dedication. Thank you. Thank you for your service. So this will appear many times on your next exam. Now, let's look at the specific line reactions. Now, for these line reactions, they were introduced in like half a page in lecture, and it was like, whoa, a lot of reactions. You don't need to know the mechanism for any of them, and they're all doing the same thing of the redox moving up or down oxidation numbers. Oxidation levels, I should say. So, let's just do a recap here. If we have a primary alcohol and we're going to an aldehyde, what oxidation level did we start at? 1. What are we going to? 2. What about a secondary alcohol, where we start at? And then a ketone? 2. Now the weirder one. If we have a primary alcohol, we start at 1, but then if we go to a carboxylic acid, we're going to 3. So, essentially, we need a version that's going to be like, hey, chromium here, we either want you to stop at the aldehyde, just go up to oxidation level 2, or we want you to go all the way and become a carboxylic acid. And the difference here is our sidekick. So if we want it to stop at the oxidation level 2, we use pyridine. If we want to go all the way to a carboxylic acid, we need water. The reason why we need water is, look at this girl and this girl. Do you see how you have added an oxygen somehow? That oxygen had to come from somewhere. It had to come from the water. So that's my like little way of remembering it's H2O versus the pyridine. It's normally pyridine unless we need to add an O, then we need water. Yeah. You can. That's a great question. So if you started off with an aldehyde and you put these reagents, you still need the source of H2O and you have your chromium oxidizer, you could go from the aldehyde to the carboxylic acid. Yeah, like if you want to, just to help think about it, you can write out a fourth reaction, which is like an aldehyde, and then the CrO3H2O, and then carboxylic acid, like this. The one thing that you can't do is you can't go from a ketone to a carboxylic acid, because then you'd be breaking a carbon-carbon bond. Yeah. And again, you don't need to know the mechanism of it. It's really cool, in case you're interested. We can talk about it later. But all of these are just line reactions. And then for lithium hydride, it is doing reductions. So you saw it reduce ketones and aldehydes to alcohols. It will also reduce carboxylic acids to alcohols. So that's going from oxidation level 3 to 1. Now, amides, it's kind of funky fresh. It's reducing oxidation level 3 amide to an amine. And, ooh, we can make an amine one other way, which is a nitrile. If we add lithium hydride, we're going to add hydrogens, and it's going to turn it also into amine. So going from 3 to 1, I'm going to do an announcement. These are the only 2 reactions in the entire course that make amines. The only 2 reactions in the entire class that make amines. So if you have a reaction where you have to form an amine, you probably used LAH. Yeah, she's our girl. Ding dong. Thank you. Technically, also, you can get an amine from, like, an imine hydrolysis. But, like, that's going to be, like, if you see an imine, you know you're in imine land. If you just see a nitrogen on a molecule, you're like, that's so fascinating. Where did you come from? She came from here. Cool. So, again, these are all, like, line reactions. So, for the practice, I pulled some here. These are going to be from Challenge Problem 3 and from Skill Builders, page 6 here. So I'm going to give y'all a few minutes to try it out. Like, I'm going to give you like 3 or 4 minutes to try out some out of this redox chemistry. And then I think one of them might have an enamine situation. And then we'll go over it. Oh, we normally end at 10. I think when I said I was going to end at 45, I mean like 10:15. Sorry. Wow, we're really out here. I'm so sorry. Yeah. Mhm.
Is it okay if I split it like this?
Yeah, you split it correctly there.
And is it okay that I write it like
That's
this?
perfect.
Okay.
What do you mean? Is it okay? That's the exact right answer. Yeah.
Yeah, but it's just like.
Yeah.
Oh, and this is too
Yeah.
awkward. No, that's nucleic acids. Oh, so you're going to make some. Wait.
Oh yeah, you have to add an O.
No, but this is not an alcohol. This is an ester. It's double addition to
Like,
ester.
for
Oh,
primary
I know.
chemistry,
We
it's
do.
about the carbon.
We
So you look at the
transform
carbon,
this
you
into
say how many other
alcohols.
carbons is it
You
connected to?
add two
And if the
H's
carbon's connected to
because
one
you do
other
the
carbon,
other thing.
and then
You can use
and then
you
you
have two
H.
carbons.
What is it called again? NADH4. No, NADH4.
Because the carbon's connected to two other carbons of the R's.
And then,
When you're making into alcohol.
wait, no, do they do double addition? No, BH4 doesn't do double addition to ester. So you
Yeah, it
do-
doesn't impact us.
So you do LI.
LH.
Log.
A lot.
L-I-H-4.
H4 ET2.
Yeah.
H plus one.
Or, yeah.
And then you
H plus
add,
one. And now
what was
it's
it, C3?
two alcohols like this.
Was it C3?
CR3 chromium.
Cause yeah.
So I'd be careful with this confusion on here. So when you double add an ester, you're definitely going to kick out. Yeah. So you're definitely going to cut here. And then that's just going to be OH2. And on this side, that carbonyl is going to turn into what?
Ooh, that was good.
I'm dubious about it working. I'm not judging.
So you're so close. Like when you double add hydrogens to a
That
carbonyl,
is actually
the carbonyl gets turned into an alcohol. Like this.
that this like
O
only
is
is
the
my
OR
R
is
is
from
probably
the
set on Microsoft Word.
That's wrong.
That's not really.
Oh, wait, you're only hiding.
Yeah, because as a carbon, you have to add two hydrogens.
Otherwise, like there wasn't space to write.
They definitely can't make the H's. I just was
So, but then I had to use Google.
No, I know I did.
But like,
Like the way this is.
Well, like, how do I go from this to this?
No, I'll
Because
change to
this
this.
is
It, so
we just we do a little ketone
and so you come now to primary alcohol, right? What reaction takes you from primary alcohol to a carboxylic acid?
We did this year.
Chromium with H2.
okay, so this is
you know,
I guess then this must be our CRO3.
And we want to turn it into and then add
Pyrimidine. Pyrimidine. Yeah. But this is pure. Pyrimidine is like when you're talking about like this pyrimidine, but this is just pure.
but how do we turn it into this?
Yeah, with CRO3, unless we need to go all the way to carboxylic acid, then we swap out the pyrimidine for H2O. Yeah. Cosmic energy.
Yeah.
Wait, I thought we had a reaction already that turned alcohols back into ketones. No, we had a hydrate back into a ketone.
For the second one,
Yeah, I think we did.
but I think it has to be a 3.
And then the dial factor is
Oh, actually, it only has to be 2. And first of all, you do CRO right? And that'll give you a ketone, and then you just say, well, sorry, not
I know, I just like answered questions and
Acetal.
reminds
That
me
is.
that
Because H
The
plus
other.
also like turns in that.
And so to do that, we
Okay,
just
so now
give it
so
R.
we did do what?
Like,
has to have gone to the
And like it's similar for the
Yeah.
first one is basically the stage, right?
even though there is an offer one.
You have to like identify the
A double bond. Turn that double bond. Am I typing?
No, and we're not take and try it. If you want to end this conversation,
What, you eating breakfast is going to end this friendship?
Okay, let's chat about them. So the first one over here, we have functional group I's. What? We have an ester. So we're already thinking double addition esters. And then in the product, we have carboxylic acids. So now, carboxylic acids we make from redox chemistry, from like oxidations, right? And what do we have to oxidize to get carboxylic acids? Primary alcohols or aldehydes. So let's just draw what the alcohol version of this would be if you had primary alcohols. It would just be a straight chain like this with all your carbons, 1, 2, 3, 4 carbons, which is like 1, 2, 3, 4, 1, 2, 3, 4, and alcohols. But here we have a folded up little boxy boy. We do have 1, 2, 3, 4 carbons. So we need to go from an ester, oxidation level 3, to alcohols, oxidation level 1. We use our reducing agent, lithium aluminum hydride.
is this because of the documentation?
Yep. So, we need a fake mechanism for going from the ester to the product of the reduction here. My fake mechanism is I find the carbon that has the OR and the double bond O. I cut the bond to the OR thing and add an H. And then on the carbonyl oxygen, I turn it into an OH and I put 2 of whatever I added. So in this case, hydrogens. So that looks a little crazy and wild, but let's do it a step at a time when we're drawing out. So after steps 1 and 2, what we should have, our carbons stay the same, but we cut this bond and we have an OH over here. OH. Then on this carbon, we need to put an alcohol, and then whatever 2 things we added, which in this case were hydrogens. And do you see how that is the thing that we wanted here to oxidize into the carboxylic acids? So all we need to do for our third step is our oxidation. The Jones reagent, CrO3 with H2O. Second one up here seems like a jump scare from exam 1. We have an acetal in the product, and then we have a alcohol initially. Acetal, let's go ahead and do our disconnection and get what the carbonyl version looks like. So our little fake mechanism here was we cut the bonds to the ORs from that central carbon. Then, to the OR side, we add H's on each of the O's. And then to the central carbon, we put a carbonyl. So we know that we definitely have to add this molecule right here. And then our question is, how do we get from this alcohol to this ketone? Well, are we doing an oxidation or reduction? Oxidation. So we use our main friend for the oxidation, CrO3 with pyridine. Cool. Then, once we are at this step, then we add in our diol with H+ to form our acetal. No third step needed. The last one down here is a little tricky. We start off with what functional group on the left? A primary alcohol. And then what about on the right over here? It's an enamine. Enamine. Ding dong. So we know only one reaction that makes enamines. That's the enamine formation reaction. And so we need our fake mechanism disconnection. So let me show you my fake mechanism for enamines. You break along the CN bond to the carbon that's going to the double bond. Then on the nitrogen side, you just put on a hydrogen. So that side's done. But now on the side that has the double bond, what you're going to do is on that far carbon, the one that's closest to where the nitrogen is, so this carbon right here, you're going to put a carbonyl. And hey, well, this already had a hydrogen on it, so that's an aldehyde. So again, with every reaction you're learning, you're thinking, yes, I need to know the mechanisms for it, for the ones that you're responsible for the mechanisms. But then also, I need my little shortcut for how do I just draw what the product is.
Could you go over the big mechanism again? I missed a second.
Yeah. So find your enamine. Cut along the C-N bond within the enamine. You don't want to cut on one of the C-N bonds that's not near the double bond. On the nitrogen side, add a hydrogen. And then erase the double bond, make it a single bond, and add a carbonyl.
And then erase the double bond.
Mm-hmm. And then add a carbonyl. Yeah. So it's pretty clear that this primary alcohol needs to turn to this aldehyde. So we're doing an oxidation. Do we do it with pyridine or H2O? Pyridine, because we're just going up to oxidation level 2. CrO3 pyridine. And then we need to add in this amine. And Logan used pH around 5, right, in lecture? Did he write like pH around 5 on the arrow?
Oh, yes.
Yeah, cool. You'll see that a lot. It means like very like mild acidic conditions, but not actual acid. Cool. Yeah.
I said my R group was just the 4 carbons and the associated H's. Is that wrong? I guess. I said, like, I don't know if you can see, like, R group and an NH2 there.
Yeah, that is wrong.
Okay. Can we just ignore pH 5?
Ignore what?
pH 5.
Oh, the pH being around 5.
I think we need to like spell it out.
So this is the thing. In the past 6 years, we've changed how we taught it and like different things. I would say if you didn't include it, we'd probably still give credit.
What happened to H2O plus? Because I thought that we needed that also.
That's for hydrolysis of these. Yeah. Here we're doing the Ford. We're making it. Cool. So that's basically the kind of redox, the kind of decisions that you'll be making. Let's move along and talk about CADs. So this is basically a page of the lecture notes that I just kind of, again, typed up, tried to make it look pretty. Yossified, thank you. That's what I was thinking, but honestly, this isn't my most yossified. This is a mild yossification, a botched yossification, if you will. So one of the important things to know about the CAD family functional groups is the relative levels of reactivity. So all of these, there's going to be an argument for each one of why they're more or less reactive. Acid chloride, she's unhinged. She's that friend that you're worried about. Like, is she okay? What's she up to? I don't know. I hope she's okay. Acid anhydride, you're not going to do as many reactions with, but she is like, she's like one drop of water could break her. She's anhydride. She does not like any water on. She's very reactive. Yeah. Whereas we also have those friends that they're just a carboxylate. They're just chilling. They're not really doing anything. They're kind of stable. They're like just working. I don't know. And then we have our girls in the middle, our ester, our carboxylic acid. And then slightly less reactive than that is the amide. So thinking about these in some way where you can prioritize the reactivities is going to be essential for doing the reactions of CADs. So I'm definitely not going to. I'm not going to talk beat by beat through this, but there is justification for all of these of why they are in this order for reactivity that I would say review and look at. But let's talk about organizing this for doing like line reactions and synthesis questions. So I have made a little chart of all of the reactions with CADs that y'all were taught. Now, with this, there are kind of two core principles that you can see here. The first core principle, everything can become a carboxylic acid. No matter what functional group we are at, we have a reaction that is going to take us to a carboxylic acid. It is our grand central station of CADS. Key fact 2 is it is easier to go down in reactivity than it is to go up in reactivity. So if we start an acid chloride, we could go directly to ester, we could go directly to amide. If we start at ester, we could go directly to amide. We didn't explicitly talk about it, but it could happen. But if we were trying to go from an ester to an acid chloride, we don't have a one-step way of doing that. What we would have to do is go to grand central station of the carboxylic acid, and then from carboxylic acid become the acid chloride. So the only one that really moves up reactivities ever is carboxylic acids. So with that in mind, all we have to do is kind of diagnose if we're going between two CADs of are we going up or down in reactivity? And then if we're going down, we can typically do it directly. And if we're going up, we have to go through carboxylic acid first. So let's look at a line reaction or two with this. Like here, we're going from a carboxylic acid to an amide. Are we going up or down in reactivity? Down. Yeah, on the other page. Again, I know it's new. I know I didn't explain it, so it's like, yeah. We're going down in reactivity, so we should be able to do it directly. So if we look at our little like spider web, if we are going from a carboxylic acid to an amide, we can do it directly with DCC. So we put DCC in and whatever amine we want, and then we can do it. So DCC, and then let's look at what amine we want. So we are going to cut here to get our amine, and we just put an H on it. So H and the N within the 5-membered ring. I mean, yeah, I guess. Like we have seen it a few times now, haven't we? Yeah. I think no, I'm gonna mess up her name. It's like Piperidine or something. Yeah, it's Piperidine, and then the version that has double bonds is Pyrrolidine. Nah, I'm probably messing all these up. I'm not sure. But yeah.
That like graph before implied that like nitrile was the only one you can't get back from once you leave, but we know other ways of getting back from it, right? Like if you went to an amine, could you get back?
So y'all don't know a way to get back, and you won't learn one in this course. A way to get back, no. So you either are going to plop on a nitrile, or the nitrile is going to get used up.
All right, so like once you leave nitrile, you can't go back.
Yeah.
Okay.
There is a way to go. We just don't teach it to y'all. Yeah. So, with those kind of key ideas in mind, I want to let y'all work on some of the practice problems. The thing I will say, so all of these mechanisms you did in lecture, and all of them you are technically responsible for, but CAD reactions are much more heavily tested in line reactions and synthesis. It's just not as heavily tested for the mechanism. The mechanism, the fundamental idea is always the same of you have a nucleophile attacking the carbonyl in the CAD, and then you do a lone pair push and you kick off a leaving group. And then you have some like protonation, deprotonations in there. But I also, I made another reaction summary sheet for you that has all the reactions. That's pretty. Yes. In the past, Logan didn't want me to give you all the summary sheets because he was like, it does too much of the studying for them. And I was like,
Wait, I still have to internalize it. I feel like it's great.
yeah.
Yeah.
Maybe on the year that the exams were open note, like on the Zoom year, with COVID, it did make it too easy.
Yeah.
Yeah.
We're
Yeah.
getting closer and closer to being able to see your previous reaction sheet in my mind.
Ding dong. Ding dong. So, here are all the CAD family of reactions. And again, I like to think of this lecture as 4 families. The first family is amine-enamine, the second family is redox, the third family is CAD, and the fourth is like amino acid peptide stuff, which we're about to talk about. So again, trying to kind of structure our toolbox of reactions. I'm going to get y'all set up with the practice problems, and then I'll circulate. So these are challenge problems 3 and 4, some selected problems, and some from Skill Builders, page 6.
Oh, yes.
And then like this is the kicking off thing.
Yeah.
Kick that off into water is like the idea.
Yeah, and that's the biologist, organic chemistry. Yeah.
In regards to like how this fits with the reactions we've learned up to this point, like yes, it's a toolbox and they're all structured, but will they ever come together? Like the
Yeah.
Okay.
Sure do.
Okay. Will we have to do like things where you go from
You'll need to do reaction from lecture 3 followed by a reaction from lecture 8 or a reaction from lecture 5 and then top it off with reaction from lecture 6.
it's like a bunch of ingredients.
It is.
I
It
see.
is. But it's like we're teaching you the grocery store. I'm like, this is the aisle that does this is the aisle that does this, and then you all have to do your own papers.
Yeah. I can bake.
You're right, Andy.
I don't know where you went.
Yeah, there's a long
Almost like mad science.
Ozzy, Maddie, Grace, Sandra, Steve.
It's probably going to use green when we're going through acid chloride for amide. Because like it says like it's like sometimes it's not and sometimes it is.
Say what?
When to use like purines when you want to
Oh, you either need to use pyridine always, or you need to indicate that you have excess amount of your base, like of your amine. Sorry, I'm stripping over my words. So basically, pyridine is a nitrogen with a lone pair that acts as a base, right? Your amine that you're trying to get to react is also a nitrogen with a lone pair that could act as a base.
Alright, so we
So-
either add a ton of it or
Yes. Yeah. So like if your amine that you're reacting with isn't valuable, it's not like a fancy amine you can just buy it at the store, then you can just use excess amine and you're fine. But if you like only have enough to do this reaction and you don't want any of it wasted, then you add pyridine.
Alright.
Yeah.
So it's just kind of like, for our purposes, if we're willing to be wasteful.
Yeah, you could do either one. Yeah. Mhm. Okay, let's talk about some of these. So here we're going from an amide to an ester. So are we going up or down in reactivity? Here, amides are going to be less reactive than any of her sisters. So we are going up in reactivity, so that means we have to go through what first? Carboxylic acid. So we're going to first come a carboxylic acid. The reagent we use from that, from our little tree, is H3O+. And then we turn into an ester with our Fischer esterification. If we break along this bond, we see that the alcohol we needed to add was this. So our alcohol with H+. Okay, ester to acid chloride. Are we going down or up in reactivity? We're going up because acid chloride, we're worried about her. She's really unstable. So first we need to go to a carboxylic acid. Then we need to go to our acid chloride. So carboxylic acid, let's do it with base, NaOH, H2O. And then once we are at our carboxylic acid, we use Sockle 2. Sockle. That's the one that has the weirdest mechanism. So just heads up. For all the other mechanisms, you can kind of vibe out. SOCl2 is the weird one. Yeah. Oh yeah, thank you. Thank you, you do. If we're doing it in base, we need an H+ workup. You're totally right. Because otherwise, if we just did step 1, we'd wind up at a carboxylate, and a carboxylate doesn't do any of the reactions we want it to. Carboxylate, we said, was the bottom of the pack. It's the most stable. It's just vibing with its own resonance. Yes. Okay. Then we are going from acid chloride to, what functional group is this in the product? An amine. We only know 2 reactions to make an amine. Not aminase, please. Respectfully, gross. So we have amine that we are making, and so we know that this had to have either come from an amide or a nitrile. Now, the nitrile, when we do our reduction, if we have a C triple bond N, that's going to turn into a CH2, NH2. And here, we have more involved things in life. Like this nitrogen is attached to multiple things. And so we know this can't have come from a nitrile. So our only option is this came from an amide. So let's draw a potential amide. Just put in a carbonyl next door. Okay, now we can think about how do we go from this acid chloride to this amide. Well, you know what, not LAH. So this, we're just going down in reactivity. We're still in our CAD family. So we're not changing oxidation level.
Oh, I thought you were saying for the next part.
Oh, for the next part. Yeah, definitely. So for acid chloride to amide, we need our amine. So we're going to cut off right here, and we'll get nitrogen in a 6-membered ring. And then we can use pyridine, or you could just write your normal amine and put XS. So that's going to get us to the amide. Is that okay so far? And then we use LAH.
Is it HR2N with a 2 at the bottom, or no? For going from chloride to
Amide?
amide.
So you have to put the specific amine. Yeah.
But do you put a 2 or no? You just
No.
no. Oh,
Where does it say you put 2?
If it's chloride and amine, H2 and
Oh, this is just a generic version of an amine.
Oh, it's not 2 of that
No,
group.
no. It's like saying that like this nitrogen could attach to 3 things. It could be a secondary amine or it could be a primary amine. Yeah, I can see how that's a little confusing. Sorry. Yeah.
You first, 'cause I had a question on the previous one.
H2.
So for the previous one, question, so you did sodium hydroxide and like water and then did H plus workup, but did the arrow say that an alternative was just in one step to do water and H3O plus?
Yes.
And
That
you
is an
would do the same
alternative.
thing?
It's okay. The thing is, when you do it in acid, you use acid to form the ester. So, like, in terms of, like, literally just, I was going to say Le Chatelier's, but that's not what I mean. In terms of the KEQ of the reaction, you get better yield when you use base, but it is valid to use just H3O plus, and you can do it in one step. That's totally fine. Yeah. Cool. Last one down here. So we have DCC and an amine with a carboxylic acid. That is our making an amide. So here we need to add 2 ethyls on here. Ethyl and ethyl. Okay. And then we are an amide. And we're doing a reduction, lithium hydride. And so our reduction of an amide, all we do is basically erase the carbonyl. And we put 2 hydrogens in the place. So what we wind up with is this girl. Triethylamine. She also can be written as NET3. Not to be confused with her older brother, which is tetraethylammonium man. Which looks like it looks like a little man.
Oh, did you just add that as action?
Yeah, this is like a different molecule, but like they are very similarly structured. Yeah. Yeah.
In your map of the, like all the Rock-Ryan reactions with like Grand Central.
Yep.
When you write, I know you talked about this, but I also forgot your response. Sorry. But in amide, there's R2 and also like in the actual drawing of it, and then but then it could also be H's. So in
Yes.
this case, does R also mean H?
Yes, in this case, R is carbon or H. Yeah, I can see why that is confusing. But then if I did H, R-H2N, then it starts to look even more insane. And so, like, that's why I just used R2 here.
What would that be?
This is, like, explicitly saying it could be an R or an H. Yeah. Yeah. But let's round off the last little section with amino acid chemistry. Amino acids, you know them, you love them. You've seen them in many other classes. But now, when they say amino acid, you know that that's an amine and a carboxylic acid. Wow. The chemistry, it's right there. That's Svita ion with the plus and minus. That's what's going to be at the pH of cells, around 7. So we need a way of making amino acids. That's going to be our Strecker synthesis. So our Strecker synthesis puts together lots of reactions we've already seen. So first step, we use NaCN and NH4Cl. The NH4 is going to come together with the aldehyde to make an imine, or in this case an iminium. It's positively charged. And then the CN minus is going to come and attack that imine. So this step of the CN minus attacking the imine, that is going to be the only kind of new curved arrow step that you've seen here. Okay, and then what we wind up with is this aminonitrile. So we have an amine and we have a nitrile attached to the same carbon. And all we need to do is turn this nitrile into a carboxylic acid by doing our nitrile hydrolysis reaction. So this is one where you could be asked to do the full mechanism for it, but like also that would be a long mechanism question. So the main way that you're going to be using this is with synthesis, I would say. Now, DCC, we've already seen here. It's a coupling reagent. And what it does is it takes the end of a carboxylic acid, the end of an amine, and says, well, go together, make a peptide bond. And peptide bond is just an amide bond. So in other classes, you've talked about peptides. Now we call them amides in organic chemistry. The issue here is, what if we have multiple things that we could connect together? So, like, for example, this is the demonstration that Logan did with the students and was like, you know, hold hands in all the different ways. Like, what if we want this, but then you could have the DCC grab, like, these two and put it together, and if we connect these two, that's going to give us this product. Or we could connect two of these with the R2 bits. Like, we could connect the carboxylic acid of one of them with the amine of another equivalent of it, and you get two R2s on your dipeptide. Or you could do the same thing over here, two R1s. There are lots of choices. So, organic chemistry, we don't like choices. We want specific products. So, we have to use our protection strategy again. So, to protect an amine, we use Bach2L. She's crazy. She's crazy, she's wild. I like the meme of, like, therapist, Bach chicken isn't real. Bach chicken can't hurt you. And this is Bach chicken. Bach, Bach,
Especially
Bach.
when the terbutals are up, it does kind of look
No, the turbutal is like straight up a chicken foot.
Well, no, when they're up,
Blah,
it
blah,
almost
blah.
looks like wings.
Oh,
Oh,
like a
Yeah.
Bach
If
chicken
they're-
trying to
if
fly
they're
and
down,
get you.
it's like weirdly
Very
straight out
that.
legs, but if they're up,
Very that. So we use Bach2O to put a Bach on our NH and protect it, and then we can remove it with TFA, trifluoroacetic acid, which you don't need to know the structure, you can just call it TFA. We don't make you know mechanisms for either of these, so these are just line reaction level. Then the way that we protect carboxylic acids actually is just turning it into esters. So that is the reaction that you've already seen of, like, protect it with a Fischer esterification, and then you can get back to a carboxylic acid by doing base with an acid workup or H3O+. So our strategy is, once we first protect what we need to protect, then DCC will only have the two things we want it to connect in order to form our product. And then finally, you do your deprotection steps. So typically in the past, on exam 2 or the final, one or the other, probably not both, there will be a synthesis that will be DCC, and it should be easy money. Because when you're doing a DCC synthesis, like 6 of the steps are already spoken for with the DCC step, protecting both of them, deprotecting both of them. There's not much more we can ask on top of that. So it's going to be a pretty, like, it's a synthesis question where you have a roadmap at least. So let's do that challenge problem, DCC synthesis, together, and it'll be the last thing we do. This is challenge problem 5. So, first thing that we do in a synthesis question is we ID functional groups. What functional groups do we have in this thing? Carboxylic acid and amine. We have an amino acid, right? We have, yeah. Then, in the other molecule, what functional groups do we have? We have an arene. What else? An alcohol. Right now, I'm only going to write out the alcohol because we don't know reactions of arenes yet. So for synthesis, the arene is just kind of like fun decoration. Okay, and our product, what functional groups do we have? Yeah, we have amide. Sorry, the pronunciation really throws me sometimes.
it is amine, and then it feels like it should be amine, but it's not.
Oh, I think it
I
should
think
be
it should be
Amine, amide, amine, aminium, hemiaminal. Hey, we're out here. And we have another amide over here. Okay. Now let's start to try to map starting materials on the product. Is there anything that you see in the starting material where you're like, I'm pretty sure it's that in the product?
Very.
Yeah, our ring. Our phenyl, not phenol.
Hey, why isn't it a reed?
Let's... This has gotten out of hand. Logan, the students are revolting. Logan, get in here. I need backup. So we have a phenyl group, and then we have a carbon that's connected to it. Those are probably going to be the same. And then we have what I'm going to call green star carbon over here, which is 1 over from that. So this right here should be our green star carbon, correct? Okay. Now, what about this other one? So here, glycine, we have an amino group, and then a nothing carbon, and then a carbonyl. And this carbonyl I'm going to call like orange star. Well, I feel like right here she is a come on girl, give us nothing carbon. So we have an amine, nothing carbon, and then a carbonyl. So I do think that that's orange star.
Well, because it's basically we have two of these amino acids connected to each other.
We do, yeah. This is the whole synthesis setup here. So we need to figure out how to connect the two amino acids, but right now we only have one amino acid. So let's make this second girl an amino acid. So this alcohol, well, we don't really have a reaction that goes from alcohol to amino acid. The structure synthesis starts with what functional group? Aldehyde. So can we go from alcohol to an aldehyde? Oh my gosh. Crazy. Let's do it. So, pH, dun dun dun. And we are going to use our chromium oxidizer. And we want to stop at aldehyde, so we use pyridine rather than H2O. Then we do our structure synthesis. So step 1 is NH4 plus, and then NaCN. Actually, I think we write it as NH4Cl, right? Yeah. We just put like counter ions with it. So then we get to the intermediate here, where we've added a CN and we've added an NH2.
Why did you get number 1 if it's just one step?
Well, because it's part of a 3-step process. Like I'm just doing 2 and 3, like this. But it's really just to show, hey, this is the 3-step structure synthesis, but you wouldn't have to do it on the arrow. Yeah. Step 2 is we do H3O plus to hydrolyze our nitrile into a carboxylic acid. And then our last step is a neutralization. So,
We can just write neutralization.
yeah. Yeah. Just in the same way you can write H plus workup. Like, I mean, H plus workup doesn't mean a reagent. It's like, you take care of it, quench it. So, from here we have our product. And when we say neutralize, we can neutralize it to whatever pH we want. We can make it here like this, where they're both like neutral. We can make it NH3 plus. We could make it to like O minus. Neutralize is like a catch-all. We don't care what the protonate state is, but do whatever you need to do to get it to the protonation state you want, essentially. Yeah.
So what did we do in these 3 steps?
This.
Amino acid synthesis.
So now we have an amino acid. We had our given amino acid. We need DCC to connect them. So the thing that we have to ask is, in our kind of glycine molecule, did DCC react with the carboxylic acid side, or did it react with the amine side on our glycine?
Carboxylic acid side. The amine side has to take our thing.
So it's because, yeah, our amine over here is left alone, so we need to protect our amine. So let's protect it with, indeed, the Bach chicken. So we put Bach 2O on. This becomes NH Bach. So now, I'll color her gray. She's locked down. She's protected. Now over here, if this one's contributing the carboxylic acid group that DCC is going to react with, then this one over here needs to contribute the amine, right? Because we only want DCC to grab one from each. So we need to protect our carboxylic acid, and we protect it as an ester. So pick your favorite alcohol.
The one.
Hmm?
The
Sure. Oh, yeah. That's going to be weird, but let's do it. So you could do any alcohol you want. Let's do the diol with H+. And there, it's going to look a little funky, but I am really here for it, actually. We'd have our O, and then blomp, blomp, blomp. So a dangly bit. Because here we're not using the OH like twice, like in the acetal we'd be using it twice. But it totally works. Like, this is protected. So you can use whichever one that you want for this. But now this is protected. We have our 2 amino acids. We are ready to join them. We want to join our carboxylic acid and our amine. So what reagent do we use as our coupling? DCC. So now, it's a little bit weird with the drawing. Yeah, like this is the step where I can just do it a little bit faster than y'all. So we still have our protected bits on the end, but now DCC has helped us make this new peptide bond. Okay. So now, to get to the ending product, we definitely need to start removing stuff. So we need to remove our Bach, we need to remove our ester. But I am now at time. I've already hit the 10:15. Do you want me to do like last 2 steps, or do you want to just...
Yeah.
You'll be done with the challenge problem then. Okay, so we need to figure out which one to deprotect first. Like this is an ester, and we're going to an amide, right? So are we going up or down in reactivity? Down. So we could do that directly. And this is one where it's not explicitly listed on the lecture slides, but I put it on the tree, my little reaction web in parentheses of like, we're going down, we can just use an amine and like pyridine. Or if you want to go first to carboxylic acid, then to amine, live your truth. So for this, we would put our amine that we are adding, so we break this, and we add a hydrogen. So this is going to be just NH3 ammonia and pyridine. So now the only thing that we need to do is remove our Bach chicken with TFA. Oh my gosh, I remember it now, and a little mnemonic that one of my students from last year thought of with how do you remember that TFA is what removes Bachs? Do you know Tina Fey, like the comedian actress? Tina Fey hates chickens. That's the mnemonic, that's the whole thing. TFA, Tina Fey hates chickens. So, there you have it. But do you see how already this was a 1, 2, 3, 4, 5, 6, 7, 8, 9 step synthesis? And like half of them were structurally doing a Strecker, protecting and deprotecting. Like we didn't have a lot of creative choice here. But thank you for bearing with me running late and everything. Thank you for coming to section. Have a good weekend. Hopefully the piece set won't take nearly as long because it is half as long. But try to get some rest and we'll have grades out on Monday.
Yay, thank you.
Woo. Yes.